Okay, in this unit we started out looking at the volumes of areas of revolution. Now we're going to take, instead of areas, we're going to take arc lengths and revolve them, and then look at the area of surface of that revolution. So we won't get a solid, we won't be finding volume, but we'll be finding area. So let's take a look at the idea of what we're working with here. Let's say we have an arc length from x equals a to x equals b for y equals some function of x. Again, we'll be very general here. And if we revolve this, for our beginning example, we'll revolve about the x-axis, but the idea holds true for the revolving about the y-axis as well. And it's actually a little bit easier to work with, as we'll see in the details here, whether we go x-axis or y-axis. But as we revolve this, well, I'll try to picture as best as possible, do my best imitation of an artist, which isn't real good, but okay, we'll have, again, this is not a solid, this is just the surface. You can kind of think of just the outside of a bowl, maybe, instead of the 3 dimensions on the inside, just the surface area here. And, well, the idea of area, we still need to think about taking a slice. Okay. Now again, the slice will be 3-dimensional, not necessarily just a rectangle, but I'll try to draw the slice over here as best as I can. Oh my. Okay. Now, really what we have here is like a ring. Okay, can you picture that? And what we need to find is the area on the outside, the surface area of this ring. Well, how do we do that? Well, we kind of have to think, what do we know about area? And if we, say, slice this out at a particular point and roll it out flat. So we take this ring, slice it, and roll it out flat. What do we end up with? Okay, we'll get a very long rectangle, and of course the width of it is just that thickness of our slice. Okay. Now, typically we would look at this and say, let's let the slice be the width of dx. But we're going to change this idea here. If we are looking at the slice this way, what were you doing, or what were you supposed to be doing in the beginning of 7.4? Okay, the arc length, this length right here, or width, this little width, can actually be represented by ds. Okay, that's that tiny little arc length from one side of the slice to the other. And that's the formula we're using for the length of the curve in the first part of this worksheet. So that's going to be the ds. But now, what's the length of this rectangle after we've sliced out the ring, chopped the ring off, and laid it out flat? What would the length be represented by?
AB?
No. Look at our three-dimensional graph here. The length would be all of that.
The circumference?
Okay, the circumference, which circumference of a circle is basically a circle, 2 pi r. Okay. Well, as we look at this, we're revolving about the x-axis, so the radius is going to be that right there. The radius will be represented by what?
S? Or
No. Well,
just f of x?
Correct. Let's call it y for now. But in terms of x, we would have to say y would equal the function, whatever, maybe square root of x, maybe x squared plus 1, whatever function we're dealing with. But technically, the radius will be the y value at that particular slice. Okay, so we think about the whole thing. What we've done so far is just the area of this slice, the surface area of this slice, the circumference times the arc length of that slice. And as we look at the whole thing now, we're going to integrate from A to B all those little slices from A clear over to B. Everything will fit into this general form. So our integral, go from A to B, 2 pi r ds. Now that's the basic formula. We got a little ways to go yet, but that's the basic idea of how we're going to be finding the area of the surface of revolution. Okay. Well, what we need to look at next, go ahead and move to the next page. So now the details, in particular, what is r and what is ds? Well, we've got this in terms of x equals a to x equals b. So if we can turn everything into terms of x, the radius we said was y, but in terms of x, that would be whatever the function is to get the graph in the first place. Okay, oops. Then ds, well, ds is the same as what we talked about in the first part of this section, the tiny little arc length here. We'll magnify it a bunch. We're looking at the, well, you could almost say a right triangle. The hypotenuse is going to be following that curve, but the smaller it gets, the closer it gets to a straight line. This is delta x, this is delta y, so delta s, okay, which will turn into ds as we make this infinite number of slices. Well, delta s I don't know what I'm doing. I keep bumping something. Delta S is equal to, we We can use the Pythagorean theorem with delta x and delta y. And, well, instead of looking at delta x and delta y, we can turn those into we're kind of redoing some of the theory he talked about in the first part of this, but I don't think some of you have gotten quite that far yet anyway. So, but technically will be, I guess this would still be squared. If we can look at it in this form, what we're really doing is changing delta s delta y squared, this right here, kind of get, and then dividing by delta x. Well, to get that delta x into the square root, delta x is the same as the square root of delta x squared. So plug that in here, and we have this square root divided by our delta x squared under the square root, and we can combine it into this, which now as we allow delta x to approach 0, that turns into the definition of our definite integral. And so ds by dx, again looking at it in this form, will equal square root of 1, this part's just 1, and then what do we change delta y over delta x into?
Just that? Oh, by the...
It's our derivative, definition of the derivative as delta x approaches 0, and then that's squared. So the ds part, now we can kind of look in terms of differentials rather than derivative notation. We multiply the dx, and that's that. So again, kind of looking at what we have here, for arc length, it is just the ds. So arc length, let me go ahead and put that on here. As you learned or will learn in the video from this,
But I don't know why you change it to that. The dy over dx to the derivative.
so arc length would be this, and the surface area well, it's the circumference times the arc length is essentially what we end up with, and that's going to be still from A to B, 2 pi times the radius times ds. But ds we can represent this way.
R in terms of x,
So
R will be
yeah,
just x?
no, in this case, where we're revolving about the x-axis, R
Is y.
will actually be y,
So then you have to
which
change-
would be the actual function. So revolving about the x-axis becomes,
So it'll be 2 pi f of x. What if it's in terms of y? So you change just to...
yeah, we'll take a look at what happens there. It's actually easier than you think. If it's about the y-axis, and we'll go that way. And in this case, kind of resembles a trumpet bell, kind of. Yeah, you got to use your imagination with my drawings, but you're used to it.
It's a-
Well, yeah, tornado. Now, the radius this time, whatever slice you take, the radius will equal the x value. Okay. Now, the nice thing about this one, we can still look at arc length from x equals a to x equals b. We can keep this in terms of x. We don't have to turn it into terms of dy. So we're still integrating from a to b.
Would it be times 2? Times this?
2 pi, no. 2 pi r will just be x. And then ds, well, it doesn't matter, ds is still going to be represented this way. So the real difference, whether we revolve about the x-axis or about the y-axis, the only difference really is going to be what we represent radius as. And either the radius is going to be y, which would be the function that we're graphing, or the radius, in this case, is just the value x. The only place where the curve, where y equals f of x, is going to show up is in the ds part when we take the derivative. So these will be the two formulas that you have to worry about, and basically just this right here will be the one formula we worry about, and then r has the two different possibilities. So that will be your surface area for this revolution of an arc length.